can you write the title down? Electric potential. Can you see that okay? Yeah. Did you write this down? Yeah. Yeah, got that? Yeah. Okay. So, let's have a look. You know when a particle is above the ground, it has potential energy. Do you remember the formula? I hope so. What's the formula for potential energy when it's above the ground? mgh. Good. Because a force is acting on it. What force in this case? Gravity, yeah. And this causes an acceleration, which would increase its speed. So what energy would it have? And therefore kinetic energy. So because energy can't be created or destroyed, the kinetic energy it gets at the end must have came from a potential energy it had at the start. So the potential at the start. Now, when a charged particle is between two plates, remember we did these examples, the particle moves. So there's a force, which means, like gravity, there's an acceleration. So therefore there must be a potential energy as well, caused by the two plates. By comparing this problem of a Q in a field to an M in a space, we could arrive at a formula. Let's have a look. Okay, so let's have a look here. Alright, so here is the ground, and here is the M, and this is the height here, and this is mg, and the potential energy would be mgh. Okay. Now let's compare it with this picture. No gravity. Okay, no gravity. What we have is a plate, a positive charge. This plate here is negative. This plate here is positive. Okay. Now, what force is acting on this? EQ. Right? Mm-hmm. So when you look at the pictures, you realize they're actually kind of the same picture. In this picture, there's a downward force. Is this force constant? It is constant. I mean, does it change? No, it's the same. And this one here as well, acting downwards, constant as well, because the Q doesn't change. Okay, so if I call this distance here h, yeah?
Even if you change it.
Well, I'm going to get into that in a moment now. We'll deal with the. I was kind of fluffing it a bit because just to make the explanation easier. It does change, but we'll get into it now. You know what? Actually, yeah. To prevent confusion, let me just put the positive at the top, and let's imagine there's a ceiling here. This is in like a room. But also here, KJ, the G technically changes as well. If you're on the very high mountain, the G is actually less. So it is. The point I was making is it's the same picture. Okay. We'll call this here H, and then down here is EQ. So you realize the picture is actually the same. There's a force causing this to go from the ceiling to the floor. There's a force causing this to go from the ceiling to the floor. So the potential energy formula would be the same. It'd be EQH. But actually we have a formula for E. Do you remember what it is for the plates? V over D.
Oh, V over D.
Well, in this case the D is H. If it's at the beginning. So here you're left with just VQ. Now, again, this is the potential energy here. If the particle is, for example, here,
It's the same.
well, no, you can't cancel this because the H and the D are different. Yeah, but we don't usually have those problems in physics. Usually the problem is it starts at the top plate and falls to the bottom plate. So actually, I think in the exam 99% it's like this at the top to begin with. So it means we have this very easy formula for the potential energy. It's the charge multiplied by the voltage. What will this potential energy change into when it gets to here? Kinetic. So of course you know then, if you wanted to, you could say VQ is equal to a half B squared, if you wanted to. Anyways, this is the formula for potential energy in a field between two plates. Got that? Yeah. Well, while you're writing it, let me just ask people to think about something here. If you compare the two formulas, the M is a property. So for example, here it's the property of the particles, it's its mass. Here, which one is the property? Which one is a feature of the particle? The Q. Okay, so these are like the properties. The H obviously has the same function as the H here, but think about this. What is the E in this formula? Field strength. So by making the comparison, we can think of the G here as being like what? Like a field strength. That will become important later. Okay, continue. So the potential energy due to being an electric field is given by the formula QEH. But of course, if it starts at the top, where the H is the distance between the plates, you can simplify it as QV, which is more common, since E equals V over D. This gives us something to think about for the G in the MGH, actually. So have you got those two formulas? Yep. Okay. A little bit of vocabulary. We call the cathode the positive plate, I think, and the anode is the negative plate. Or do I have that backwards?
Is it the negative plate?
Yeah, it sounds wrong, doesn't it? Wait, before you write that down.
Yes, opposite.
Yeah, no, this is one of those things.
Iron is positive, but cathode is the negative plate. Yeah, it's opposite.
No, our friend Google will prove us all wrong or right. For the moment, just leave a space. The cathode is the blank plate, and the anode is the blank plate, and we'll double check it now. What? Cathode is the negative one?
Negative.
Flip.
How can we have both? It's saying the negative charge direction.
Hold on, Google will answer.
Opposite is the iron.
Parallel plates, which is the cathode? I need one that has it. Not this one.
If unknown or negative is tested.
There you go. Here, can you see the positive charged plate is called the cathode?
Because it is negative.
Because
So-
ions are
It attracts positive. Okay.
English is a problem. Oh, maybe it is backwards. Because this one says the positive ions move up to the cathode.
Oh.
So that means the plate must be charged negatively. Stupid English. It's very confusing.
Yes.
Well, you did this in chemistry, didn't you?
No.
No.
Oh.
Yeah, in high school.
What?
Yeah. Yes. Cathode is negative charge weighted by its positive terminal in the decrement to the
Oh.
negative valence without that is positive because it attracts the electron.
But then in this picture, the cathode is the positive plate. Because if you look at the current, and the anode's the negative plate.
even the definition.
And in this picture, the positive is going to the anode. This picture is the opposite
That is a true.
to this picture. Can you see that?
What is true?
That is a very good question.
Only for K charge or positive ion, cathode is positive.
Yeah. Cathode is positive.
Is it though?
Cathode and anode are opposite of cations and anions. Anions are positive.
In primary battery is positive.
Is
Positive. In
which cathode or anode?
Cation is negative,
Cathode.
cation is positive.
Cathode is the positive plate.
in different in
So
a
you have
battery.
got now, right?
Oh,
It's
different
positive.
names. So I just care about the one for the fields. Anode negatively, cathode here. But that's what the battery you said. We might have to. I might have to check this in an actual book, which I should do. I just thought I could get an answer here easily. It seems not. That's sad. Very sad.
What about just cathode and
Plate. with a negative charge on the small and positive charge on the small.
Let's see. Cathode positively charged. Oh, sorry, that's a negative. Anode positive.
Yeah.
Anode positive. Cathode negative.
But in
In a capacitor, but a capacitor is the same thing as the parallel plates for the electric field. Because remember we said we can make a capacitor by putting two plates close together, and we can also make an electric field by putting two plates close together. So I have it backwards, I would assume. The cathode is the negative plate.
the cathode is negative.
Yeah. In the parallel plates.
Almost like battery.
Yeah, but battery is different though.
Battery is negative. Is positive.
Possibly, I don't
Yeah.
know. I just need to know these words for the fields.
What are they different in battery and positive?
I call it the positive and the negative plate since it prevents confusion. But because but the electrolytic tank is different to the plates. Like
in tank is negative. In battery is positive.
yes,
It might check here.
Yes, I will believe you.
So-
I believe you.
So not a part about the plant.
So I think this one is wrong. It should be the other way. It should be the cathode is negative and the anode is positive for the plates. The only reason is I just want to give you the vocabulary, but it's not something to worry about because in the exam obviously there's a picture, so you know which way around the plates are. But I better fix it. It's so frustrating because I would have told the students last year the cat one was the negative one, and I decided to type it and I typed the wrong thing. And the way I remember it is that cats are bad, so that's the negative plate. That's how I remember it.
Oh.
What's a cat?
The animal.
Oh, okay.
The cat and dog. The cat is mostly.
Yeah, that's like a Chinese cathode. It's like a zebra.
There's my thing gone.
That's how I remember.
Wow.
Where is it? There you go. The cathode is the negative plate and the anode is the positive plate. Alright, let's continue. That was a pain. Right, remember, if the potential energy is positive, what does that tell us about the particle? It's moving. It has energy. It's moving. So we say the charged particle has potential energy. What does it mean if the potential energy is zero? It's free. It's a free particle. And interesting, negative potential energy tells us what about the particle? It's trapped. Yeah. Then we say the particle is trapped in a potential well. Also remember that h would be the distance from the particle to the plate it's attracted to. Just remember that the h is not the distance between the plates, it's the height to the charged particle. I said this before in what lesson? Where does this slide look familiar?
PE and KE.
Yeah, in which lesson? The mechanics. Huh? What?
Stickman.
The stick man, yeah. My stick man falling from the sky. You don't remember my stick man for this lesson? That's it, yes. Yes, that's good. Have you done energy levels in chemistry?
Yeah.
No? I mean with your current teacher, not last year.
No.
What are you doing? Are you doing the labs at the moment, aren't you? Organic, okay, yeah.
Teacher,
Yes.
when we calculate the h, do we take like here to here or here to the middle?
Technically it'd be to the middle, but because the particle is so small, you don't need to consider its radius. But technically it'd be to the middle of the particle. It's center of gravity, I suppose. Continue? No? You don't have to write everything down. You just have to say potential energy greater than zero has energy. Equals zero, free. Less than zero, trapped. Yeah, what does trapped mean?
Yeah, this is
Not free. Continue? You know what trapped means because you've done ionization in chemistry. So what is ionization? Yeah, to free the electron. So if you're given it energy to free it, it's because it is trapped, because it has a negative potential energy. Yeah, but it's trapped. You need to give it, to free it, you need to give it energy. So it has a negative potential energy to begin with. You give it enough energy to get that to zero, then it's freed. So for example, if the charged particle had -1 joule of potential energy, then you're required to ionize it, you must give it 1 joule of energy so it can be freed. Yeah.
Before it ionized, it is trapped.
It's trapped, correct. It has a negative potential energy. Was this not said to you?
No.
No.
Because it's generally.
Yeah, well, whatever the cause is, and in this case it's attracted to the opposite charge, it's still trapped. Okay, continue.
Yes.
So the conservation of energy means that the initial energy of the charged particle must equal the final energy. So we can have E1 equals E2, and we know that the kinetic plus potential must be equal. Nothing to say here, you know this already. So since we have this PE equals QV, and Q is so small, well actually no, just perhaps I should also say to finish here, quite often you'll end up with a situation where it starts at rest, so this one would be 0, this one here would be, it would be QV, the maximum, QV. This one here, no, this one, a half mv squared, and this one here, 0 if it hits the bottom plate. Yeah, if it goes down. Okay, there is not a problem, but the potential energy of a charged particle is very, very, very small. You know what's coming next. We don't use joules to measure the energy, because the energy is so small we'd have to use like 10 to the minus 12 joules. We'd have to use a really small unit like this. So we don't use joules because Q is so small. We use a different unit to measure energy. We use something called an electron volt. This is, now before you write anything down, an electron volt is just a very, very small amount of energy. It's like a tiny, less than a joule of energy. How much energy is it precisely? So the definition is 1 electron volt of energy is the energy gained when 1 electron is accelerated by a field of potential difference 1 volt. So what I mean by that in a picture before you write anything is if you have 2 plates and here there's 1 volt and here there's an electron and it moves down here. This here has a potential energy which is equal to QV. This energy, we call this 1 electron volt of energy when the V is 1. When the V is 1. So actually if the V is 1, then how much is 1 electron volt of energy? Well, it's whatever the charge is of an electron, but what is it, 1.67? Minus 19, thank you. Basically that's how much 1 electron volt is this many joules. I never remember these things because I just remember it's constant 23 on the calculator, so that's all. In my head I'm just remembering this number. Okay, so you can see that 1 electron volt is a tiny amount of energy. This definition is a pretty common definition on the exam, and it's not so difficult to remember. 1 electron volt is the energy 1 electron has when it's put into a field of potential difference 1 volt, and it accelerates then. Yeah, so if you can write this definition down for sure. Come on back there. Whoops. You have this definition, could you? Could I have another strawberry? Have you got any left?
Yeah.
Ah, no, that's your one.
No, he already has it too.
Because I had 2 as well.
No, it's okay.
But I'm bigger than you. So maybe I should have 3. I'm 50% bigger than you, so I should have 50% more. I'd say I'm 50% bigger than him. What's your mass?
That's so weird.
I.
50?
If you're in the 50s, I'm more than 50% extra.
100?
About 100, yeah.
I'm kind of sure.
So,
Yes.
Oh, really?
so are you saying you're half my mass?
Yes, what the
More than half.
You're more than half. You're 50 something.
Yeah.
Okay.
Wow.
I'm 51.
51?
Well, it's supposed to come here. I'm 61. No, I'm 51.
You lost 10 kg.
Yeah, I still eat a lot.
It's brain power. Burns calories.
I have to
Huh?
Why is this
Couple of kg would be okay, I think. Yeah.
I was there.
Okay. You got this?
100.
You're not 100.
100 G. 100
55.
Okay, we'll continue. You got this? Yep. Now, here's a small question for you to try. Convert 1 electron volts into joules. It should only take you a few seconds to do.
Oh no.
How many joules in 1 EV? Yeah. It's 1.
0, 9,
Yeah.
5,
10 to the minus
18.
19.
Oh, 19.
Yes. Okay, well here's the other one now that's more interesting. I want you to convert 1 joule into electron volts. So should this be a big or small answer? Big. Because there are many electron volts in a joule. Yeah.
242.
Okay, you have an answer there?
Yeah.
Lee, what did you get?
6.242 times 10 to the power 18.
18, positive, yeah. Can I just show you on the calculator what you would do is just do 1 divided by 23. So that is that answer. Yep. Okay, here is a more interesting one. Again, I think you should be able to do this. You have 2 plates and they're separated by 2 centimeters and 500 volts between them. An electron leaves the negatively charged plate on the top and accelerates towards the positive plate down the bottom. How fast will it hit the positive plate? So you have 2 plates, a negative and a positive. The electron leaves the negative plate and fires down to the positive. How fast will it hit the positive plate? You definitely do not need to... Well, no, I won't say definitely not. You probably don't need to consider the gravity force.
Why?
Because I feel like... No, actually, I shouldn't say probably or even definitely. I don't know. I feel like you won't need the gravity force, but you better include it just in case.
But we get different answers if we change.
The answer should be practically the same because I feel like the acceleration caused by the plates will be huge compared to the... Anyways, I can just tell you, Lee, for these types of questions in the exam, when you have electrons moving between the plates, they don't include the G. But I wonder if we do include it, how different the answer would be. I'm not expecting it to be much different. Huh? QV equals a half mv squared. So it'll just be QV plus mgh equals a half mv squared. Oh, the mgh will be tiny because the mass of the electron is tiny. The Q is small, but the V is quite big. Yeah, I know in the exam they never include gravity. I actually let's try this without the gravity. So, okay, here's the plates. Here's the electron. This one has energy QV, and when it gets down to here, it has a half mv squared. So QV equals a half mv squared. So 2QV over the mass square root is the answer.
Yeah.
Now that V is velocity, voltage. Okay, let's see what we get here. Square root 2 times, it's an electron, so it's E, times 500 over, now which one is the mass of an electron? Is it number 3? Yeah. See, it's a huge answer. It's huge.
But what's the D distance?
Yeah. Isn't it interesting? I didn't actually need the distance between the plates because it wasn't in the formula. So I didn't actually need to know the distance. Which I know it seems strange because you think if you change the distance you should get a different answer. But you don't actually. If it was 1 centimeter, it still hits it at the same speed.
How? Electric field varies by distance. So.
Well, imagine this. If we halve the distance, the electric field will be stronger or weaker? Stronger. So will the particle accelerate faster or slower? Faster. So will it be going faster or slower when it hits the bottom plate? Well, no, because although it accelerates more, it has a shorter distance to accelerate. In total, the reduced distance balances the increased acceleration. So the end result is the same final distance at the end. It's like if you have a race and you shorten the distance but make the person run faster, their speed at the end might still be the same. Guys, I'm curious to see would the answer be much different if I did include the plus mgh. And you can see, Sean, then I do need to know what the h is. I think so, but let's just check, okay? So the only difference here would be this would be 2 times qv plus mgh.
They are acting the same direction.
Yeah.
Oh, okay.
Yeah. Plus G H. I can't even tell if that's even different.
No.
Is it like exactly the same?
No.
1, 3, 2, 6.
No, it's exactly the same.
It's exactly the same.
It's not.
1, 3, 2.
It's
I
like
thought-
it's 400 ms different.
No, it's like 13262051445.
Yeah, it's the same. It's the same number.
Either 13261.
Yeah.
So it's like 400 ms different.
400.
Okay, but because the numbers, so the first 4 digits are the same, 1, 3, 2, 6.
Yeah.
And for the exam answers, you need to match it the first 3 significant figures. So in other words, my point is this is so small we can cancel it from the energy. It's like 10,000 times smaller than this, or 100,000 times smaller. You know, it's a lot smaller than. Okay. So what's interesting here, as Sean saw, was in fact the distance is not important, and in the exam they often don't give you the distance for these problems, and sometimes students at first think, oh no, I can't do this because I don't know enough, but you actually don't need to know the distance. Okay, an electron enters a field which is at a potential difference of 10 kilovolts. The electron accelerates across the field until it hits a proton which is at rest on the positive plate. The electron binds the proton and they move off together. The plates are 4 centimeters apart. How fast do they move? Well, what I'm picturing here is you have a negative plate and you have a positive plate. So, you know, this is maybe some kind of metal, obviously, and this is metal here. And an electron leaves this plate and fires down. And when it gets into the plate, we picture maybe there's a proton. I suppose maybe I shouldn't say one proton, because if it's a metal, what's the metal with the smallest number? Protons. Lithium, yeah, it has 3 protons, doesn't it? Although, could you make it? Yeah, lithium plate. Yeah. So, okay, maybe in real life the electron will hit a lithium atom which is made up of 3 protons. But just in my example, to make it a little bit easier, I just said the electron hits 1 proton. So the electron hits this proton, and what happens to it? It attaches to it, click, and then because it was moving very fast when it hits it, what happened? Then this moves off. Faster or slower than the V the electron hit the plate at? Slower. And my question is, if I call that V, I want to know what, if I call that V1, I want to know what V2 is. How fast do the two move away together? Do you understand the question? Yeah. Well, here's the story anyways. You can try this and I'll do it now. Just give it a go. I think you can do it. My beautiful picture? What do you need from my picture? There's nothing useful in this picture, is there? I think you got everything here. Okay, kids. How's this? Okay, alright. Cool, man, cool. Like a cucumber. Got an answer, Bruce? No? Do you know what to do? So why no answer if you know what to do? It's on your calculator. Lee, can you open the lid?
No, it
doesn't have constants?
Yeah, I have for this child. But we have right before. Teacher, is it exam with the math given? Because it is not on the calculator.
Well, the math is not. Maybe it's not on that calculator, but it is on the Casio one.
Oh, it is.
Anyway, to answer your question, Lee, the math, all these constants are in the formula book on the front page, so it is provided. It's just easier if you can just hit a button on the calculator to get it. You know. Let's have a look.
Wait. Almost done.
Did you get an answer, Sean? Oh, okay.
What you have done for me, what is MD constant in each F3?
Yeah?
Yeah.
Okay. So, this electron has potential energy of QV, and that should equal the a half m v squared here. So, we got the v equals, like we said before, 2qv over the mass square root, which I might even have still 2, yeah, what's the v here? 10,000. Okay, so that's the velocity. It's large, isn't it?
Yeah.
Yeah. Now, I won't write that down, I'll just keep it on the calculator. What do we need now for the next part? The conservation of momentum. M1, which is the electron,
Yeah.
times V1 plus MP0
Yeah.
equals,
ME plus
yeah.
MP.
basically X ME plus MP.
Yeah.
Yeah, the V2 if you want to prefer.
Yeah.
So it means that the V2 will be ME V1 plus,
No.
yeah, over ME plus MP.
Yeah.
Okay, well that's actually okay because this is the V1. So I just need to multiply this by the constant. So ME is number 3, isn't it? And then ME plus MP. 32.3 kilometers per second.
Yeah. Like,
Yeah, they go. Yeah, the speeds are huge for fields.
Will we feel it if it's 2 hours?
Nah, because the mass is so small, the momentum is tiny. It is good that your instinct is to stick your hand in front of it to see what happens. This is a good natural physics instinct, you know. I wonder.
I will die.
Now, I'd say your hand would just become charged as it's hit with electrons, so it'll become negatively charged. I think that's all that would happen. Okay, did you write this down? Yeah. I wonder what would happen if I... do you have the original speed? What was it?
Oh,
no.
120? Okay, well I won't need to point that. No, I'm just wondering how different the answer would be if I had it strike a lithium. A lithium atom would, the only difference is that the mass would be 3 protons. That's the only difference, isn't it? Yeah, so I'm just wondering, it'll be smaller, but still, it'll be, instead of being, yeah, roughly divide by 3. Instead of being 32 kilometers per second, if it struck a lithium atom, it would be about nearly 11 kilometers per second. So, still pretty fast. I actually do like the idea of it striking a lithium. So I think for the January students, I will change it to a lithium. Until it hits 3 protons at rest on the positive plate. Yeah.
Bound to the proton.
Thanks. You see, this is how come I have typos in my slides. The electron binds to the protons, and they move off together. Did I actually need the 4 centimeters for this one?
No.
No. Let me delete that for the next students.
Why not? Confuse them.
I already confused them once when I had it in the last question. The plates are some distance apart. There now.
Oh, this is more confusing.
Yeah, there. Nice. I like it. Okay. All right. Let me see. Let me see. Yeah. Yeah, I think this is all okay. These ones, 1 to 5 is going to be easy peasy. It should only take you a couple of minutes. Number 6 is a juicy one. Just before you try them, I just want to draw the picture for number 6 so you know what's happening. So, a battery is connected to 2 horizontal plates. One plate becomes positive and the other plate becomes negative. The electron is fired at 45 degrees under the negative plate, which is above the positive plate. So, actually I shouldn't really have said under, I should have said on. One plate becomes positive. An electron is fired at 45 degrees from the ground. Hold on. I'm confusing myself. The positive plate lies flat on the ground. That's what I want. I drew it backwards here. I want it like this. And what you do is you fire an electron. So, in other words, I wanted it to be pulled down by the positive plate. So it'll go up, just about miss the negative plate, and come back down. Yeah. And then here, this has a voltage. And I don't tell you what this voltage is. What do I tell you? I tell you the distance between the plates is 10 centimeters. So that's 10 centimeters. And I also tell you the speed here is 1,000 meters per second. Yeah. And this is 45 degrees. Now, what would happen if I make this voltage really, really big? What would happen to its path?
Stronger gravity.
Yeah, well, like, describe its path. Would it still look like this? No. What would it look? It'd be more like that, wouldn't it? And what happens if I reduce the voltage?
Fly higher.
Yeah, it'll go straight up here. In fact, if I make the voltage 0, then there is no field anymore, and the electron will just keep heading that way. It only stops because it hits the plate. So my question is, what is the right amount of voltage so that it goes up, just misses the plate, and comes back down? There must be some right amount to just about get this path. It does exist. Try that one after you do 1 to 5. But this is the picture, what it should look like for 6. So maybe just draw this picture and then start 1 to 5.
Do we consider gravity?
Yeah, like we saw earlier, if we did consider it, it doesn't affect our answer when we're calculating to 3 SF. Technically there is a gravity force acting down, but because the mass of the electron compared to its charge is so small, that most of its force, 99.99% of the force acting on it, is caused by its charge, not its mass. So we can ignore gravity for this one for sure. I don't know if I put this on Moodle, I'm sorry. Forgive me.
I think
Okay.
Do we have paper for the exercise?
Dude, I told you, I'm so busy. I'm going to try and print it out soon.
Why you're so busy?
Because I'm the most important, valuable teacher at the school, and they have me do a lot.
What is that?
You know what?
I'm an important
That is
teacher.
nonsense.
I'm an important teacher, and they make me do a lot. So I have very little time. This school would fall apart without me.
Oh, okay.
Could you get more paid?
No.
It takes us 5 minutes, but okay.
No, it doesn't, because I have to copy it into a Word document, and I have to put in, like, you know, pictures and links and references and...
Here's the difference.
This guy? No. I couldn't ask him.
Who?
You.
Me? You what?
Okay, do you all have these questions? You can take a picture on your phone if you want. I'd like you to try these now. I think if we don't have a break, we can finish a little earlier then.
Yeah.
Would you rather a break?
Yeah, ask Steven, physics. Come on. Teacher, why is the rainbow in color when you say photo?
Hi.
It's what?
What? Nothing. Watching
Come
too
on,
much Breaking
You
Bad.
have to know that.
Do you want to take a break? Or do you... Okay. Alright. Well, can you just maybe take a picture or you know, because I need to close this, so... You got it?
Ah, okay. Send to the group.
Why me?
Yeah.
Color.
They do have answers of this.
Yeah.
The answers
Yeah.
are only on YouTube. You will have to Google this lesson and look at the video from last year. That's what I mean. I can't just copy it into a Word document. I'd have to work out the answers so I can type the answers in as well. So I have not written the answers down anywhere for these questions that I've made up. Huh? You can't find the answer if you type... Huh?
Yeah, that's what I'm saying.
Yeah, like that's the reason why it's not as quick as you think, because I would either have to solve it or watch the video from last year with the answers in it. If I want to print this out, I would like to print it out with the answers on the back.
Yeah?
From last year, of course. Yeah.
This question not in Moodle.
It's not?
It's not in
I don't know. I'm sorry, look. Next week will be a lot better than this week. I have so many things to do before Friday.
Oh, coursework too.
Yes. They're
Oh
giving,
my god, you're fucking...
yes. They're giving me a hard time over the coursework. They haven't approved it yet.
Because we have many questions.
You have many questions?
How about you will?
You mean the
Yes.
previous coursework or the coming one?
No, the coursework too.
Oh.
They haven't. The Manchester haven't approved it yet for me. So, and the
No,
physics.
the coming.
That's the coursework physics.
They haven't. My point is, the reason I'm not doing the labs is they haven't approved the labs yet for me to do. Yeah, I know, it's a pain. It's a pain. So I have to submit a report on what labs I want to do with you, and they have to go, change this, do this. So then I have to change it. Then I have, you know, it's just, if I could, I would do the labs maybe this week, but I can't. I have no power. Powerless. Can I close this now?
Yeah.
Yep.